if you know the values of an analytic function only on the boundaries of a simply connected domain, you can compute all values of f inside the domain too. The information on the boundary is already sufficient. But how do you do that? Well, with Cauchy's integral formula. You will see the formula and two examples in this video. So, how does this read? If C is a simple closed contour, taken once in positive direction, so counterclockwise, Z0 any point inside C, and your f of z has to be analytic on inside C. Then you know f of z0, you can compute the function value somewhere inside your domain. You have to integrate, you take as your function numerator f of z and denominator z minus z0, dz. And you have to divide by 2 pi I. So, let's take a look at the picture. We have our C, simply a simple closed curve, our z0 somewhere inside C, and then we can compute our f of z0 using this Cauchy's integral formula. So let's do an example. For example, if you have f at e to the power it given by 4 plus e to the power 2 it, so it's given on the unit circle, then you can compute f of 0, you can compute f at the center of the unit circle. So how do you do that? F of 0 equals 1 over 2 pi I, you integrate along the unit circle, your f of z, dz, and you divide by z minus z0, which equals z. Then you parameterize, so you keep your 1 over 2 pi I, take z equals e to the power it, so t runs from 0 to 2 pi, dz becomes e to the power it dt. Here you have the z from your function, and you divide by, you have f and evaluate at e to the power it. Then we can simplify a bit, of course. Those values, those numbers cancel out. You can take out the I, which cancels out, so you're left with 1 over 2 pi. Integrate still from 0 to 2 pi, and you plug in what your f is. That equals 4 plus e to the power 2 it. So there we are. Then you just have to integrate with respect to t. So integrating e to the power 2 it will yield e to the power 2 it over 2I, and plugging in 0 and 2 pi you get the same. So that's, well, cancel out those contributions. And if you integrate 4 with respect to t, you get 4t, and the upper boundary gives you 2 pi. So you get 4 times 2 pi from that integral, divided by the 2I which we had in front, equals 4. So we have the information on the boundary, and we know the value which is in the center, or you could have taken any point as at 0. It's usually not used this way. Usually Cauchy's integral formula is another way. For example, to compute horrible integrals, like this integral over here. Integral on the unit circle and then of some horrible function. However, the function is not that bad because it's analytic except that z equals 0. So what you can do is you choose your analytic function, cos z over z squared plus 9. You choose your z0 equals 0. And as you see, you choose, of course, the unit circle. And then with this choice of f, with this choice of z0, you see what happens if we apply Cauchy's integral formula in that case. Well, we get z0 equals 0, so we get f of 0. You get your 1 over 2 pi I. And then if you plug in those data, you get exactly this f times 1 over z minus z0, so 1 over z, which is exactly the integral which you want to compute. So you can compute this integral, express this integral in terms of the function value f at 0. So your integral becomes 2 pi I times your function value at 0. Well, it's easy, you can just plug in 0 into f, which gives you 2 pi I over 9. So Cauchy's integral formula is often used to compute integrals in terms of single function variables. And that is why it's really nice, because now you can compute integrals without the need of computing antiderivatives. You can, for certain functions, use Cauchy's integral formula.